Hello, everyone. Welcome to Thermo Fisher Scientific 4D STEM webinar series. This is Çiğdem Özsoy Keskinbora, Product Marketing Manager at Thermo Fisher Scientific. We have Professor Roberto dos Reis with us today. He will talk about the general overview of 4D STEM principles, key data collection techniques, and the data analysis. Professor dos Reis, holding his PhD in physics from Brazil. He was a postdoctoral fellow at NSEM Molecular Foundry, Berkeley. In 2018, he joined Northwestern University as an assistant professor, and his research interests include advanced characterization utilizing scanning transmission electron microscopy. He is also responsible for the introduction and adaptation of the direct electron detectors in Northwestern University, and also integration AI in electron microscopy data analysis. After this short summary, I would like to give the stage to Roberto.
Thank you very much, Ignan. Thanks again for the nice introduction and for inviting me to give this talk. So the idea of this talk for the Thermo Fisher for this STEM webinar series is that to give a brief introduction of the methods, right, for these STEM methods, and a little bit of applications, and also give you a kind of like a roadmap how to collect the data and how to set up your microscope for that. So later in the series, you're gonna have more like about like experiments and like how to actually like collect the data. So I hope this gives you a little bit of some insights about that. So the goals of that, so I summarize here, is just that to have the attendees to leave with the foundational knowledge for the STEM, especially like focusing on application like the how to acquire the data and how to manage data, which is a big problem in this field too. And the learning outcomes I listed here. So to understand the principle of STEM, the basics of for the STEMs, also important things that identify the applications of that for these STEM methods. Master the data acquisition, right, to understand how to acquire the data, and then apply this practical consideration for experimentation, basically like how to understand the technique and how to implement that in terms of like designing this experiment that you want to conduct. And also explore like data management strategies. So I would like to start with like a brief introduction to STEM, because this is basically like the foundation of 4D STEM, right? So if you know how to conduct the STEM experiments, you are like in a way to understand how to do 4D STEM properly. So starting with STEM, so we start with the convergent electron beam probe at the top. So this is represented by this green line here. So if you don't have any samples or anything in the way of the beam, so what you see in the back of your panel or your camera, you're gonna see just the green disk, basically, right? Depending on how you set up the microscope. The moment that you insert a sample, you do start seeing like a scattering, right? So it could be a polycrystalline sample, a crystalline sample, or a amorphous sample. You're gonna see a scattering of the electrons through when you pass through the sample. So these are typically called like convergent electron diffraction patterns. Right? So if you have a crystalline sample, they're a little bit easier to identify. These patterns can be collected directly on the camera, independent of the camera that you have, or it can be those electrons that pass through can be collected on an annular dark field detector, typically, right, in STEM, or in a bright field detector, BF detector. In STEM, also you can add some analytical information. For example, you can get some analytical information, for example, like backscattering, right? So on X-ray backscattering with the EDS detectors here, and energy loss spectroscopy with the EOS detector. So this is kind of the basic machine that you're going to be operating for your 4D STEM experiment. So more about the STEM, when you collect images in STEM, you have like basically like three different contrast mechanisms. So you have the mass thickness contrast to obtain like general morphology of the samples that you are observing. Z contrast that depends on the atomic number, of course, usually like acquired with like high angle annular dark field detectors, and diffraction contrast for like crystallographic information like defect analysis, etc. So all of this is included in your STEM analysis. Each will also be included in your 4D STEM detection. So jumping on the basics of 4D STEM, right? What is 4D STEM? So I listed here like four different important pieces of it. So you have to understand how to set up your electron beam, right? So depending on your experiment. So what is the strategy to scan your sample, right? So if you want like a larger field of view, like a smaller field of view, higher resolution, lower resolution but larger areas, how to configure your detector, and how to manage your data and analyze at the end. Starting with the basics of for the STEM. So imagine you have like your sample here. This is the simulated data. This is a Y and X axis here on the real space. And for each pixel in this image here, you have a diffraction pattern. So if you turn to the reciprocal space, you're going to see for each one of the pixels, you have a convergent being electron diffraction. Right? In this case here is a high resolution image or high resolution simulated image. So you do have a convergence angle that is a little bit higher. So you do have overlap of the disks in the diffraction plane. Moving to the reciprocal space, you have the QX and QY, right? And those four dimensions form the 4D STEM data set. So the important point here for 4D STEM is that we enhance the image capabilities, like beyond the traditional 2D images, because now we are collecting more information, meaning that you don't leave the microscope only with images, but you leave with the images, the real space images plus the reciprocal space, which contains a lot of information about sample characteristics, properties, etc. With that, you have the ability to analyze the material's properties at the nanoscale, like including like defects, for example, strain, electronic structure, and then you can name it because you basically have all the information about the sample in your diffraction pattern here. And then also you add the capability to capture like dynamic changes in materials under like different conditions. If you add even another dimension here, time, right? So if you can do this in situ, for example, applying like biasing, cooling the sample, heating the sample, applying pressure, etc. So the first topic that I want to tackle here is the electron beam parameters, right? So the two main points here that I wanted to go through is that one is the convergence angle, and then the apply electron dose and the dwell time that you apply to the microscope when you scan the sample. So I usually like to start this part of the talk like with showing this convergent beam electron diffraction image. This is one of the first ones they're actually published. This is back in 1938. So at that time, you have too much options to tune your conversion beam, right? So you have very limited like aperture sizes. Vacuum was not very good, so you have to operate with like much larger beams, etc. The lenses are not very well developed. There was no aberration corrections at that time, but still you could get like a very interesting patterns that you carry a lot of information about the sample. Two things that basically like evolved over time. One is that the ability to collect better or like a variety of different setups in the microscope, right? Changing the parameters. Two, the ability to detect with like better detectors. Right? Those are the 2 points that kind of evolved over the last century, basically. The first thing that I mentioned was the convergence angle, right? So depending on the sample that you want to analyze or the type of information that you want to extract from the sample, you might apply like a different convergence angle. In comparison to this one here on the left, this is a traditional select area diffraction in the TM mode that you get like a very parallel beam and then very like separated spots like this, right? So more like a spot pattern. So as you change the alpha or the convergence angle here, you can obtain like a different configurations of your electron probe, meaning that you can go from this Kossel-Mollenstadt pattern, which is more like a little bit more parallel beam, up to like a Kossel pattern, which is a very large angle, right? That is used, for example, for like strain analysis in a large angle CBED in the past. So by varying these characteristics of the probe, you can probe different properties of the sample, right? It depends what you wanted to, what kind of information you want to extract from your material. For example, right? So this is based on works that they're done using like conventional CBED, right? Which is like also another like a pillar for 4D STEM. One thing that I would always recommend is just go back to earlier papers on conversion being electron diffraction, see what the researchers at that time tried to get with like one point only, right? Meaning like they would converge the beam in a specific convergence angle and extract some information from that. For example, here in this particular example, you can extract like thickness, right? So going from like a thinner part of your lamella here to like a thicker part, you can see the dynamic reflection showing, and then you can determine thickness from here. Another possibility is looking at the lattice strain using like large angle CBAD in this case here, right? This is a typical case that where researchers use conversion beam to analyze strain in semiconductor devices. Another possibility here is just a point group determination. There's like a lot of work done in this field to probe like space group and point group in the specific points of the sample, right? So, and this was done again using like point by point characterization. And then today with 4D STEM, we can actually do like a map of this point groups. For example, if you have multiple variations of point groups within the sample, you can map that. The last example that I want to show here is like a phonon structure, right? There's a lot of work done in the past again with like looking at the phonon scattering, and then these days I've seen like more and more people trying to do retrieve like a phonon structure or phonon characteristics of the sample using 4D STEM. Oh, for example, atomic vibration, for example. Another important point here is the dose that you apply, right? And this is like attached somehow to the size of the probe that you utilize, meaning like the convergence angle that you apply in that specific experiment, right? So you can see here the typical way to calculate the dose is like following this equation here, where you have the dose directly correlated to the beam current your microscope utilize, and the pixel width, right? That assuming a square pixel. And the pixel width here is like how basically like if you keep some of the parameters unchanged, for example, the probe size and the probe current, you change those by changing the magnification, for example, right? So the magnification, you change the number of pixels per per view space, in a way that you reduce or increase the dose. And this is a nice plot just to show like how that changed with the spot size, right? In a typical STEM configuration. Of course, this can be a little bit different for depending on the microscope that you use, but it's more or less like the rule for all STEM machines. One of examples that you have to be a little bit more careful with the dose that you apply is that for like beam sensitive materials, right? So this is a nice example from folks in Berkeley that they published this in 2021. So where they did like for different beam sensitive materials, like from protein chrysolite to like polyethylene that's very sensitive to electron beam. So most of this data was acquired using a more like parallel beam, where the alpha is a little bit smaller. One way to from one side to map a larger area, but also to reduce the dose applied per pixel size, right? So you can extract like a very interesting information. For example, like you get atomic structure using like the diffraction pattern here. You can do orientation mapping. You can do structure visualization, like using this nice way to plot like flow lines representing like different stacking of this polymer, and also obtain like RDF or radial distribution function. One thing that I wanted to point out here is that when you lower the dose, you get more and more sparse data, which becomes a little bit more difficult to analyze as well. And you have to come up with different strategies. For example, like some sort of like machine vision or careful analysis of the background, energy filtering, and other methodologies that people are working on these days. But it's still possible to control the dose that you apply by changing the convergence angle, as well changing the probe size, and change the step size that you apply during your experiment. Another nice example here is that showing like this orientation mapping in this conjugated polymer, where you can see like those diffraction occurring, then you can follow them and map how the orientation works. Again, very sparse data in comparison to like a typical analysis on a more robust material, for example, like inorganic like semiconductor. Another nice example here from the literature is that, again, like as it gets more sparse, the data needs a little bit more, a little like better analysis, like I would say, right? So meaning like careful consideration of the background, etc. In this case here, following like signal enhancement protocol, the researchers here could extract this like domain maps of this like crystallites in the polymer, in a crystal polymer this case. So this is the first step, right? So to show a little bit of how can you control the dose, how can you set up the microscope, and how can you change the convergence angle, change the dose, analyze the material at different conditions, etc. So one important point here, which I mentioned in the beginning, was like how to scan the material, right? And this is very important because this is actually like when you're in front of the microscope, you do have all just like now what can I do, right? So how I'm going to scan the material in a way that I'm not going to damage and I will get meaningful information out of my diffraction patterns. So the excision parameters should be like carefully selected based on what you want to achieve or what the question that you want to obtain. Three typical ways to do it actually. Like one, you do some sort of like undersampling, right? Where you have this is typically like a low mag approach, where you have like a larger step size when this like a smaller probe. Say for example, you set up a microscope for a high resolution image, and you scan in a low mag way, right? So if your beam is like very focused in one point in a nanometer size probe, for example, and then you scan in steps that are like more than nanometers. Right? So you cover a large area, but you undersampling, meaning like you underdetermine like the position of the sample, which is still okay for many different cases where you want to obtain more like a large field of view plus information in more like in a grand scheme, like saying the sample only varies in a large area. You don't need like a sub-angstrom mapping in this case. On the other side, you can oversample your sample, like oversample during the experiment by, in this case, you have like your probe, your step size is smaller than your probe. For example, you have a 1 nanometer probe, you scan in like half nanometer, for example, right? So this is typically the case for high resolution images. And then later, we're gonna see like example for differential phase contrast, right? When we do need like oversampling to obtain like those like nice high resolution distribution of the electric field or magnetic field of the sample. So it really depends on the research question that you want to answer here. So another important thing is that more and more important now is like how you configure your detector, right? So what type of detector that you have, what's the best that you can obtain from that specific detector that you have in the microscope, independently of what detector or type of detector that you have. So the two main type of detectors, mechanism for detections, is like this. One is the scintillator detector, right? This is the one they're like either CCD camera plus scintillator or CMOS camera plus scintillator. So you do have the main characteristics that they're usually like a lower readout noise compared to direct electron detectors, relatively slow, but you can get like many pixels. That's one of the difference that you see around. Another important thing here is that you do have one thing to keep in mind is that you have like the scintillator which like reduces the sensitivity but increases like dynamic range. So that's one of the problems of direct electron detectors, which is like the dynamic range for diffraction patterns. It's something that is one characteristic that you actually want to enhance in those detectors, especially to collect diffraction patterns. That brings us to the other type of detector, which is like the direct electron detectors, which is basically like electron being generates like this electron hole pairs inside the detector. One of that type of detector is this like pixel array detector or like hybrid pixelated. Those are the ones that are like the fastest today in the market. And then you have here on the bottom right, so how they're built. Basically, they have the sensor chip bounded to separate the electronics chip that allows it to go faster and do this parallel readout for each pixel. But one message that I want to pass here is that independently of the type of detector, you can always change the parameters of your microscope to get the maximum of that, right? So I've seen, and then you can also find works in the literature that use detectors like this, scintillator detectors for 4D STEM, and many examples in direct electron detectors. And both work depends on the research question that you wanted to answer. Right? Don't be discouraged if you don't have a direct electron detector. That's the message that I want to pass. Another important point that I mentioned in the beginning is that how to manage the data, right? So as you can imagine, and I showed you earlier, that you do have now data sets that can get easily to like half terabyte, right? Depending on the camera that you acquire the data, depending on the size of the area or the area of the sample that you want to analyze, and the configurations that you utilize in your microscope, right? And that becomes a problem to analyze. And this is a nice plot that I'm showing you on the left from a review published in Nature Materials in 2020 that shows how the data generated by the cameras like really exponentially like exploded in the last like 2 decades. And that becomes a problem, I would say like a good problem, right? Because that allow us to reinvent the way that you analyze the data in a multidimensional way, especially for like user facilities or like labs that generate that amount of data. You do have to find solutions for that. So one of that is like how to store the data, right? And one way is that you have to centralize that in a way that you can facilitate the access, right, and the management. So the users typically want to access that like in an easy way and rapidly. And then also think about how to scale that, right? So if you have one user today operating your microscope and you have like 10 users in a year from now, how are you going to scale that? So imagine dealing with like 200 terabytes an hour here, for example, this extreme case, up to like petabytes of data in a day or a week. The next topic here is that how to process the data, right? So you do have to have access to high performance computing. You can, of course, do many of the analysis in your laptop, but I would recommend you to do like just a portion of it in your laptop for not to not burn that, but also have access to some of the high performance computing like GPUs, etc., and access to like parallel processing to speed up the data analysis. The other methodology that can be applied here is the data reduction techniques. So, for example, compress the data to reduce the storage requirements and reduce the data dimensionality too. You may not need to keep all the data or all the raw data if that is if 80% of that is not meaningful to your research, right? So you can, of course, store that in the cold storage, but the one that will be accessed more often is the one that carries more information about your sample. So you want to think about like data reduction techniques in this context. Another important point here is the automation in how to handle the data. So how to save that in a rapid way and actually put that in your data pipeline in your lab or in your user facility, in your center, etc. So you do want to reduce error rate and then improving like efficiency in data transport and data analysis at the end. And then to some cases, real-time analysis can really help in terms of like determining if the data is good for further processing, right? That's something that is typically a problem for 4D STEM. So you acquire a lot of data first, analyze, and then you decide how much data you're gonna keep. So ways to like do real-time analysis will be very beneficial in this case here. And visualization, of course. So you want to be able to make like nice plots that convey the message that you wanted to summarize from your sample and answer at the end the research question, right? And of course, one important point is like data security and integrity. You don't want to lose the data in this process. With that, I would like to conclude my talk. Thank you again, Thermo Fisher, and I would like thank you, Chigdem, and I hope you like the webinar and the webinar series. Thank you.